Hi everyone. Um, let's talk about linear regression. So, what is linear regression? Um, it's a big topic, but today we just talk about simple linear regression. Okay. The idea is that we have two variables x and y. Okay. We're trying to explore how x and y are related, right? For example, a common regression in economics, you will see how the income is related to education, right? Is how is return on education? Is it more educated people earning more, okay? And how much is this return, okay? It's just relation, but doesn't say causality, okay? Because having more education may mean that the person is more smart, but can be doesn't imply causation. Having one more year in school actually translate to higher income, but maybe the higher income people want to spend one more year. Okay, there's no causality, but just correlation. Okay, and the idea here is with data. Okay, and data point, because x and y, so it's paired data point. Okay, it's a pair x1 y1 the first observation, x2 y2 second observation, up to the end. The nth observation is x and yn, so it's a pairs. Okay, and what we want to do, what we mean by simple linear regression, is trying to find a line, okay, that a straight line, okay, trying to fit all the point in the best way. With the best, the many way to define, we focus on the simple one. We define clearly. But what we want is to find a line. It is y. The formula is y equal to alpha plus beta x. Alpha is the intercept. Beta is the slope. Okay, we're trying to find the best line that is find alpha and beta, such that this try to explain the best. Okay, how x and y related through this equation. Okay, it doesn't mean x cos y, okay, or y cos x, but x and y related in this way. Okay, there's no interpretation of how whether x cos y. If you want to say whether x cos y, there is something beyond what we cover here. We need more evidence trying to show if x cos y. Okay, and here we say simple linear regression. By simple, what we mean is there is only use x and variable y. Okay, you are not trying to use more than one variable. Okay, if sometimes you want to use x, z, a, b, c, a lot of variables to explain y, then it's no longer simple. Okay, it's more complicated. And linear, it just like say we are trying to relate them by a line. Okay, not a curve, not a other thing, but a line. So that's why linear. Okay, look at the graphic. It's easier to visualize this by scatter plot. Okay, you can see data here is x and y. Okay, and the green dots are the data points. Okay, if we want to fit it, okay, one of the things you may think the black line is fitting this pretty well. Okay, doesn't seem to be little. It is fitting pretty well. It's fitting passing through the middle of it. What the middle I don't know, but it's a nice feature of it. Okay, but how this line comes about looks pretty good, right? How do we fit this line? Okay, the idea is what we call the least square method. Okay, and you have to some criteria, right? That's what you mean by the best. Here is trying to minimize the sum of vertical square difference. Okay, what's mean the vertical square difference is looking at how y, okay, above or below the line. Okay, y minus alpha minus beta x. Okay, this is the proposed line. Okay, the black line, and the yi, the green one. Basically trying to see the difference between the green line, green dot, and the black line. Okay, the difference. Okay, and square it. Square means no matter you above it and below it are treated symmetrically, is above. Okay, and the further away you penalize more, so that's why it's square. So it means that if you deviate a lot, you penalize a lot. So this looks like a good criteria. Okay, you add up all of them and square. Okay, so using calculus, you can show what is the best alpha and beta using calculus because it's quadratic, so it's not difficult to see. We'll show it immediately after one slide. And what it is the beta will be a fraction, okay, which is xi minus x bar y minus pi multiply, okay, sum of it, okay. If you see this is very close to the covariance, you don't divide it by n, right? And the denominator is exactly the sum of square of x, right? And this is actually the variance, right? Basically means covariance over the variance, okay? And the alpha, okay, is basically, you can see is y bar minus beta hat x bar, okay. So basically saying that actually the regression line actually passes through the y bar x bar, right? So that's why this relationship holds, right? Because what we want is to have y equal to alpha plus beta x, right? This line. So if you pass through the mean x bar y bar, then this relationship holds, and that's why alpha is equal to this. So basically the line, the least square method, will say the line will pass through the mean of the point which is y bar x bar, okay. So how do we prove this least square coefficient, okay? But before that, let's see the diagram, right? There will be a line here, okay. Above is blue, up below is red, but we treat blue and red symmetrically, so we always square the difference, the distance between vertical difference between the line and the point, and add them all up, okay, and try to make sure that the line minimize the distance, the square distance between the point and the line, the vertical line, okay. Of course, there are many ways why you use the vertical line, but not perpendicular. There are many ways, but we just focus on this vertical definition because there's a lot of nice property here, and later we will show why this is one of the nice property. Okay, so now we are going to show you why this. We say the calculus. We're trying to show you this as the derivation of this. So the d. So we differentiate this expression, okay, respect to alpha and beta because it's quadratic. So that's why we can just differentiate alpha and beta, right? If you differentiate alpha, right, you can see this is square will come out because by the chain rule, and alpha minus 1, okay. And beta we are getting the same square, but when we differentiate beta with xi, okay. So that's why you're negative 2 because it's square, the alpha here, okay. That's why you have this, okay. From the first expression, you can take the sum of the alpha to the other side, okay, and divide both sides by sample size n. That you will left is alpha hat minus y bar minus beta hat x bar, okay. Again, repeat, is you put the sum of the alpha on the si and divide both sides by n, you get this expression. And the second expression, okay, you put the alpha hat in, okay, that we replace with this, okay. And now this expression looks a little bit untidy, but we just need to make beta the subject, okay. So what you do is you collect beta hat on the one side, right? Beta hat, okay. Okay, it's x bar minus xi and xi, right? So this is the other side, and this is y, right? With yi minus y bar xi, okay. And you make beta hat the subject, right? To divide this on the other side, so that's why beta hat is equal to xi times y minus y bar, right? Same as denominator, okay. And this is equivalent to what we have here. Why? This we'll talk about in the next slide. This is a usual, very convenient technique, okay. So let's show you why we can rewrite in this way, in this fraction. Okay. Now look at this, xi minus x bar square, sum of it, okay. And what you can do is you can write it, right? Multiply xi minus x bar, alright. You distribute it, right? It's xi minus this and x bar minus this, okay. And you can say x bar is a constant, right? Bar doesn't change with I, so x bar taken out, right? Which is xi minus x bar, and sum of it will be 0, right? Because you minus this divided by n, right? Actually, this is x bar, so this guy is gone. Okay, so that's why we left this. So that's why this expression and this expression the same. Using the same technique, we can show they are the same. Okay, that's end of the basic introduction of least square.